All right, in this section, we're going to take a look at alternating series. And these are just series that has terms that alternate in sign. So it'll be like positive, negative, or vice versa. We can tell if we're looking at an alternating series because the terms, like the nth term, will include a factor of either -1 to the n, or -1 to the n minus 1, or -1 to the n plus 1, I guess, right? That factor of -1 being raised to a power makes the sign switch back and forth. If we have an alternating series, our work is a little bit easier in determining convergence. So that's what Theorem 23 says is the alternating series will converge as long as the terms are monotonic decreasing, so they keep getting smaller, and the nth term approaches 0. This is really interesting. Like usually, right, we could use the nth term test to determine if a series diverges, but never to see if it converges. And Theorem 23 tells us that if we have an alternating series, that all of a sudden the nth term test is now sufficient to show convergence. Again, with the caveat that we also show that it's monotonic decreasing. So we're going to do some examples. Let's see what happens with this series. So we want to figure out whether or not the series whose nth term is given by n over -2 to the n minus 1 converges or diverges. And I'm going to start just by rewriting it. So, you know, we don't see that -1 to the n power show up, but it is couched in there, right? I mean, it's a -2, which means, you know, -2 is -1 times 2. We can kind of peel off that factor of -1. And that's an important thing to do when you're going to use this Theorem 23 to determine convergence. You want to peel off the alternating part so that you have that -1 raised to a power multiplied by terms that we know are only positive. So this series, as given, we can rewrite. I'm going to peel off that factor of -1 to the n minus 1. You know, we were peeling it off in the bottom, but of course, since it's -1, we could throw it up top as well. We could throw it up top instead, rather. And if we like, you know, we could kind of just get a sense for what this series is and maybe find the first few terms. So if n is 1, then let's see, -1, that would be -1 to the 0 power, so it starts out positive. And then we have 1 over 2 to the 0, which is 1. So I guess actually our first term is just 1. And then the next term is minus 2 over 2 to the first, plus 3 over 2 squared, which is 4, minus 4 over 2 cubed, which is 8, right? And it goes on and on. So this looks like 1 minus 1 plus 3/4 minus a half, and so on. So we're going to check a couple of things now. Usually the first thing I will check is that do the nth terms approach 0. It's important to note, you know, in Theorem 23, we have to make sure that both of these conditions are met. So you do have to check the monotone part. Often the monotone part requires a bit more work. I check the nth term part first because if the nth term doesn't approach 0, I know it diverges, and, you know, because of the nth term test, and then there's no need to check whether or not it's monotone. So I usually check this part first. So let's evaluate this limit as n approaches infinity. And again, I'm going to scroll back up just for a moment. Notice the way it's written here, the nth term, or the limit as n approaches infinity of a sub n. That's after we've peeled off the factor of -1 to the n. So I can ignore the alternating part here. Meaning that when I set up this limit, I just need to look at the limit as n approaches infinity of n over 2 to the n minus 1. Right, just that part there. Now, this is type infinity over infinity. We can use L'Hopital here, and first I'm going to just rewrite it by switching these to continuous functions, so x over 2 to the x minus 1. Now that I'm seeing them as continuous functions of x, that means that they're differentiable, and we can apply L'Hopital now. So we get 1 over 2 to the x minus 1 times ln 2. And now as x approaches infinity, the top is staying put, the bottom is blowing up, and so this limit is 0. So the nth term does in fact approach 0. Now I'm going to bother checking for the monotone part. So what I'm trying to check, and again, we ignore the alternating part here. I'm really just taking like this part here that I circled in blue. I'm just looking at that part and saying, if I look at those terms, those successive terms, are they monotone decreasing? So I want to know, does this inequality hold? And I'm going to go ahead and just put absolute values just to emphasize that we're ignoring the alternating part, even though in the language and notation of the theorem, just writing a sub n is automatically already ignoring that alternating part. But just to kind of emphasize that. So the an plus 1 term. So I'm just going to replace, I'm going to take this part that I've circled in blue, replace n with n plus 1. So I'll get n plus 1 over 2 to the n. Is this always less than or equal to n over 2 to the n minus 1? So I'm going to clear denominators. I'm going to do that by just multiplying both sides by 2 to the n. All right, so now those cancel. This cancels and becomes just a factor of 2. So is n plus 1 less than or equal to 2n? And now I'm just going to gather all my terms on one side. I'll subtract 2n. And so this is negative n plus 1. Is this less than or equal to 0? That, I'm no longer going to write a question mark. That is very clearly true for all n greater than or equal to 1. So now that both of these conditions are met, it's monotone decreasing and the nth term approaches 0. And that's enough for us to conclude that this series converges. Oh, let's try another one here. We want to determine the convergence or divergence for this series. Very clear right away, we could tell it's alternating. We got that negative 1 to the n already kind of peeled out. So let's check. Does the nth term approach 0? So let's look at the limit. And again, I can ignore the alternating part when I set this up. So we're going to look at the limit as n approaches infinity of n over ln of 2n. Again, both the top and the bottom blow up, so I want to use L'Hopital. I'm going to rewrite this as the limit as x approaches infinity of this continuous function. The top and the bottom are both differentiable. So now we can apply L'Hopital. So 1 over, and then the derivative of ln 2x is 1 over 2x times 2. Those will cancel. So we have 1 over x. This is the limit as x approaches infinity of x. And that is, I think, pretty clearly infinite, right? As x blows up, x blows up. So the terms don't approach 0. Not only don't they approach 0, the terms themselves blow up, which means that this series diverges. All right, and you know, we've shown the nth term doesn't approach 0, right? So there's no need to check to see if it's monotone. We know what happens with this series. Let's try another one. This is another one that's pretty clearly alternating. We've got that factor of -1 to the n plus 1 already kind of peeled out. So we just need to check, does the nth term approach 0? If it does, then we could check to see that it's monotone decreasing. And if that is true, then we'll have convergence. So let's look at this. The limit as n approaches infinity. I ignore the alternating part, so I just want to look at this limit. 3n plus 2 over 4n squared minus 3. The top and the bottom both blow up, and you could use L'Hopital here, but also, you know, some algebra just works. So we can multiply the top and the bottom by 1 over n squared. And when we do that, distribute on the top, we'll get 3 over n plus 2 over n squared. And on the bottom, when we distribute, we get 4 minus 3 over n squared. So each of these kind of fractions here, those all approach 0. So the top overall approaches 0. The bottom approaches 4, which means this this fraction, the limit, is equal to 0. So the nth term does approach 0. We could check that off. Now we are going to bother with figuring out, is it decreasing? Are the terms, like the positive terms, again ignoring the alternating part, are those terms decreasing? Now there's a couple ways we could do it. You know, in the one in this example, we just did some algebra and we checked to see if this inequality held, or for what values of n it holds, and we were satisfied that it held for all those values of n that are at least as big as 1. There's another way to check to see if something is decreasing, though, and if I asked you back in Calc 1, how do I tell if a function is decreasing, everybody would answer, oh, you just see if the derivative is negative. So I'm going to look at the continuous differentiable function that I get when I just replace n's with x's. And we could take that derivative and see for what values of x is that derivative negative. So we're going to use the quotient rule here. So on the bottom, we're going to have g squared, or the square of the denominator. Up top, we've got the bottom times the derivative of the top minus the top times the derivative of the bottom And we could do some, let's see, I'll distribute the 3 and then the 8x, so we get 12x squared minus 9 minus 24x squared plus 16x. Minus 16x. So combining like terms, we get negative 12x squared minus 16x plus 9 over 4x squared minus 3 squared. I'm going to just peel out the negative, and for some reason I switched the sign again. So that's a negative 9 here. I'm going to switch it on the end here. I'm going to factor out a negative. So here's our derivative. And we should note that the bottom, we're squaring some stuff, so that is always positive. And the top, this is always negative as long as, you know, for values of x that are greater than or equal to 1. We can get confirmation of that. One way to get confirmation of that is you could, you know, throw that in a graphing calculator and see. But, you know, this derivative will be negative for these values of x, which means that f prime of x is negative for x greater than or equal to 1, which means that 3n plus 2 over 4n squared minus 3 is decreasing. So here we have our series whose terms are, or at least the absolute value terms are monotone decreasing, and the nth term approaches 0. And that's enough for us to get convergence. It's important to note that checking these, you know, getting convergence, this is only true for the alternating series. This alternating series converges. Without that factor of negative 1 to the n plus 1 out in front, this series actually would diverge, and you could show it by using the integral test. The integral test doesn't actually apply to an alternating series because, remember, with an integral test, your function has to always be positive. You could show it with the integral test, you could show it with the limit comparison test. Multiple ways to show that the series you get by taking just the positive, you know, removing the alternating behavior, diverges. All right, our next theorem is on, we call it the alternating series remainder. Now, alternating series, when they converge, they do so pretty quickly. And if you're, let's say you are approximating the sum of an alternating series by taking partial sums. Maybe you're like, I want to know, you know, I know this series converges. I don't know how to tell exactly what it converges to, but maybe I get an approximation by adding the first like 10 terms together or something, and I see, you know, what it appears to be approaching. If you do that, then as it turns out, when you approximate the sum by taking a partial sum, then the remainder, like the maximum possible error you might be off by, is no bigger than the first neglected term. So what that means is let's say I approximate the sum of a series, of an alternating series, by adding like the first 7 terms together, then my error is no bigger than the size of the 8th term. You know, that first neglected term, the first term that I didn't include when I was finding a partial sum. So in example 532, this says approximate the sum of the series with an error of less than 0.001. So I want my error to be no more than 0.001, or I want it to be less than 0.001. So what I'm going to do first is find what is the first term in the series that is less than 0.001. I'm going to find the first term that is less than that value, and that's my first neglected term, and then I'm going to find the partial sum of all the terms below that. So we're going to find n so that absolute value of a sub n is less than 0.001. So just ignoring the alternating part. That means that I want 1 over n factorial to be less than, oh whoops, I omitted a 0.0001. So I want 1 over n factorial to be less than, I'm going to write this as a fraction, 1 over 10,000. And in order for that to happen, that means I need n factorial to be greater than 10,000. So if I just find some factorials, you know, just compute n factorial for different values, like 5 factorial is 120, 6 factorial is 720. So they need to be a little bit bigger than that. Let's see, what is 8 factorial? Let me open my calculator. So your calculator can compute factorials. They're in the math menu. So let's say I want to find out what is 8 factorial. So I hit 8, I go to math, and then over to the prob or probability menu, and it's option 4 here. So that's 40,000. Let me check 7 factorial. Okay, yeah, so looks like the first factorial that's bigger than 10,000 is 8 factorial. So 7 factorial, that was 5,040. 8 factorial is 40,320. So that means that n is going to be equal to 8. That's the first factorial that's bigger than 10,000. That means that a sub 8 is the first term in the series that is less than 1/10,000th. And that means that I'm going to approximate the sum using the first 7 terms. It should be noted, and before I actually do the approximation, it should be noted that 1 over n plus 1 factorial is less than or equal to 1 over n factorial, which means it's decreasing. And the nth term does approach 0. And I guess that would be something that's good to do first. Because if you don't know if your series converges, then why would you approximate it? So we do have convergence. So now we'll go ahead and approximate using the first 7 terms. So S7, let's see, the first term. When n is 1, that's negative 1 to the 0, so it starts out positive. We get 1 over 1 factorial, which is 1. When n is 2, that'll be a minus 1 over 2 factorial, which is 2, plus 1 over 3 factorial. 3 factorial is 6, minus 1 over 4 factorial, which is 24, plus 1 over 5 factorial, which is 120, minus 1 over 6 factorial, which is 720, plus 1 over 7 factorial, which we found was 5040. So the 7th partial sum, if we throw all this in, so we get 0.63214. So we would use that as our approximation. And that is off by no more than 1/10,000th. In fact, it's off by no more than 1 over 40,320. All right. So now we're gonna finish by talking a little bit about absolute and conditional convergence. So Theorem 25 says, if the series I get by taking just the positives, maybe I have a series with both positive and negative terms, that could include, that obviously does include alternating series. It could also include series whose signs change, the terms, the signs of the terms change, but maybe not quite in the alternating fashion. But if you take a series and you just make all the terms positive, if that series converges, then your original series has to converge. So, for example, here's a series. Actually, this is a great example of a series that is not alternating, but the signs of the terms do change. You know, sine of n, as n increases, you know, that goes from positive to negative, but, you know, not necessarily in plus minus plus minus plus minus fashion. So we'll just note that this is not alternating. But they're both positive and negative terms. So what we're going to do is let's consider this series where I just take the absolute value, sine of n, over n squared. Now, since the absolute value of sine of n is no bigger than 1, for all n, then we know we can make a comparison that this series, absolute value, sine of n over n squared, this is less than or equal to the series whose terms are just 1 over n squared. Right, this is a convergent p-series. So using the direct comparison test, we know that the series we get, or that this series, absolute value of sine of n over n squared, converges. And that means, using Theorem 25 here, that the series without the absolute values, sine of n over n squared, also converges. All right, so talking about absolute and conditional convergence, in fact, I'm going to go back to Theorem 25 here. If the series of the absolute value terms converges, then the original series converges, and in fact, we say that it converges absolutely. So that's what absolute convergence is. Like, let's say I have a convergent series. If that series that converges, if the series still converges, if I just make all the terms positive, then we say that that series, this one here, is absolutely convergent. If I have a series that converges, but then if I take the series with just the absolute values, if I make all the terms positive, but that series diverges, then our original series, we say, converges conditionally, or it is conditionally convergent. So we're going to end with a couple of examples where we examine absolute and conditional convergence. We should note here, so we've got this series. The terms are given by, on top, we have -1 raised to the power n times n plus 1 over 2. Now, if you take a look at this, it almost looks, we see -1 to a power, which suggests that it's alternating, but it's actually not alternating. The signs change in pairs. That's okay though, it doesn't bother us, but it's just good to note that we can't use the alternating series test. We could find the first few terms. If n is 1, we get -1/3. If n is 2, we get -1/9. If n is 3, we get +1 over 27. If n is 4, we get +1 over 81, and so on. So let's look at the series we get by just taking everything positive. So the series of absolute values. Now, when I take the absolute values, that removes all the sign changing that might happen, right? That -1 raised to the power n plus 1 over 2, that just goes away. That becomes 1, right? Because that's the absolute value of the numerator is just 1. So this is the series 1 over 3 to the n. And in fact, I'm going to go even further and write this as the series 1/3 to the n. Now, this series is geometric. It's geometric with r equal to 1/3. And so, of course, the absolute value of r is less than 1. And that means that it converges. And that means that this series that we started with converges absolutely. It's important to note that while, this series, when we made everything positive, we got this geometric series, we know how to tell what that converges to, right? We have that formula. We know that that'll converge to a over 1 minus r. We don't know what this converges to. And that's okay. We know that it's absolutely convergent, but it's just good to observe that we don't have that formula to use, because this one is actually not really, not geometric. All right, let's do one more. This is alternating series. So I got the -1 to the n over ln of n plus 1. So this is alternating. We could take the first few terms, get a sense for what's going on. When n is 1, it's negative, so we have negative 1 over ln of 2 plus 1 over ln of 3 minus 1 over ln 4, and so on. We should note this series converges. It's alternating, so we can use the alternating series test. It's not too hard to show. The limit is 0. You know, the limit as n approaches infinity of 1 over ln of n plus 1. That is equal to 0 because the ln function continues to increase without bound. Also, it is decreasing. 1 over ln of n plus 2 is less than or equal to 1 over ln of n plus 1. So it does converge. The question is it absolute or conditional? So what we need to do is look at the series we get when we take positive terms, or we make all the terms positive. Now, when we're applying the absolute values, it should be noted that when n is at least as big as 1, ln of n plus 1 is positive. So applying the absolute value is just going to make the numerator equal to positive 1, which allows us to write it in this simpler form. So we could see that this series actually will diverge and we could tell this series diverges by using the direct comparison test. So by direct comparison with the series 1 over n, right? We know that that's the divergent harmonic series. So the series we get by taking the absolute value of all the terms, that series diverges, and that means that the series we started with, this alternating series, converges conditionally.